Welcome back to Elements of Chemistry. In this video, we're going to talk about the basics of nuclear processes. In the next video, we'll get into specifically nuclear equations, and then the following one, we'll talk about half-life and so on. Okay, so as we remember from our discussion of the history of the atom, Antoine Becquerel was the one who discovered natural radioactivity while he was studying fluorescence. His students, the Curies, were the first ones to isolate a radioactive element, and they're credited with naming the term radioactivity, as well as in naming the emitted particles and energy alpha, beta, and gamma. So what happens in nuclear? The nucleus is an extremely dense region of the atom. Most of the mass is concentrated in the nucleus, and the rest of it is pretty much empty space because it's got those just little electrons flitting around. The protons, which is our atomic number, and the neutrons, the number of those, mass minus atomic number, aren't always the same. Some unstable nuclei are going to emit particles and or energy in order to become more stable. So what makes a nucleus stable? Well, we've got some conflicting things happening here. We know the nucleus stays together, but why? Well, the protons are repelling each other due to what we call Coulombic repulsion. Remember, likes repel and opposites attract. We've also got gravitational forces, but these are very, very weak. Due to the small mass of the particles, it's essentially irrelevant. The weak nuclear force can't help because that's what causes protons to decay into neutrons and neutrons to convert into protons by changing their flavor. Yes, it's called flavor of their quarks. So what does hold that nucleus together? The attractive forces have got to be greater than those Coulombic attractions. So we have what's called the strong nuclear force. This causes protons to be attracted to both protons and neutrons to be attracted to neutrons and protons. So the strong nuclear force acts as the glue that holds the nucleus together. So atoms are most stable when the number of protons and neutrons are equal. For example, in carbon-12, it's a very stable atom because it's got 6 protons and 6 neutrons. Its neutron to proton ratio is 1. And you really need to keep a track of this neutron to proton ratio. There is something called magic numbers. Yes, that's a real term. These are nuclei that have 2, 8, 20, 50, 82, or 126 protons or neutrons. These atoms are generally more stable than anything else, and this comes from the nuclear shell theory, not Bohr's electron shells. This is nuclear shells. Okay, if you have even numbers of protons or neutrons, they're generally more stable than odd numbers. Kind of weird, but works out that way. And we've developed what we call the band, the belt, or I like the aisle of stability. So the red line indicates where your neutron-proton ratio is 1 to 1. And if you look down at the bottom, down here at the very bottom, where you've got small atoms, most small atoms are stable because their number of protons and neutrons are the same. And as you get larger, they tend to vary from this 1 to 1 ratio. Down in this lower region, they're going to want a beta decay because their mass isn't that far off of the stability. It'll beta, give off an electron. That's going to lower the atomic number. Increase the atomic number. Say that backwards. Way up here at the top, these are going to want to alpha decay because they need to lose mass to go down. Alpha has a mass of 4. These guys down here, they've got to get more protons. So they're going to either positron emission or electron capture. So you predict the type of decay based on where the atomic number is. Atomic numbers greater than 82 are going to have that neutron to proton ratio. They're heavy. They need to get that number down. So they're going to alpha decay because an alpha particle is going to give off the most mass. If the neutron-proton ratio is too high, remember the goal is 1, you're going to lose a neutron. So it'll beta decay. In a beta decay, a neutron is being converted into a proton. If the number is too low, below 1, you're going to beta or beta positive or even electron capture to convert a proton into a neutron. So let's look at our main particles. You can have an alpha particle, which is a helium nucleus, no electrons. It's got a mass of 4 and atomic number of 2. So that top number you see here, that top number is the mass. And that bottom number here is the atomic number. And that's going to be really useful in equations. Now here you see that alpha symbol. It can be shown as 4 over 2 He or just 4 over 2 alpha. Please note there is not a fraction bar in here. We're not talking about a ratio. A beta particle is an electron, so 0, essentially massless, -1 e, or 0 over -1 beta. These are high energy electrons that are ejected from the nucleus. A positron is just a positive electron, same mass as the electron, but 1 unit of positive charge. Proton is essentially a helium nucleus, so 1 over 1h or 1 over 1p to say it's a proton. A neutron has a mass of 1, no charge, so 1 over 0, and we use an n for the neutron. And a gamma ray is just given the symbol gamma. I also see it in a lot of equations, 0 over 0 gamma. And this is just a high energy electromagnetic radiation. We call it a photon. So to summarize, alpha is a helium nuclei emitted to lower the mass of the parent to the daughter being a lower of 4 mass and a lower of 2 in atomic number. Parents decay into daughters, and then you'll have an ejected particle. A beta particle is an electron ejected when a nucleus decays and it leaves behind a proton. The daughter will increase in atomic number, but the mass will stay the same. A positron is a positive electron that's ejected from the nucleus when a proton is converted into a neutron. The daughter nuclei is going to have the same mass, but the parent's going to decrease in atomic number. Proton decay, the daughter will have lost 1 in AMU, and the atomic number will also drop by 1. A neutron decay, the daughter will have lost 1 AMU in mass, but the atomic number will be the same as the parent because we're not changing protons in that one. Gamma, there's no charge in mass, no change in atomic number. It's just a change in energy, and this is usually accompanied with a particle emission. So in our nuclear notation, and we already kind of went over that a little bit here, that top number is mass, the bottom number is the atomic number. So this is what we call isotope notation or symbol notation. We can also list it as the name with a dash in the mass, or even the symbol with the mass if we're in a hurry. So that was the basics of getting us started into our nuclear processes. I hope this helped. And in the next video, we're going to talk about how to do the actual equations with alpha, beta, and gamma, positron and neutron. And as always, stay curious, be safe, be kind. Have a great today and a wonderful tomorrow.